And okay, um, I guess I'll start today. Share my, I'll open a window and I'll share the screen. Recording, that's fine. Share it. Okay. So today is the third lecture, third live interaction session. But let us just quickly do um, a recap of the last lecture. Um, Let me introduce myself. For those of you who are just watching the third video straight and skipping the first two, let me just introduce myself. I am Shri Sahai Gupta, a PhD student at IIC Bangalore. I'm a fellow, Prime Minister Research Fellow, um, and as part of that fellowship, I have to deliver some TA-ship duties every year, and as a part of that, I am doing the TA-ship for this course, the NPTEL course of Gas Dynamics. I'm born and brought up in the city of Agra, Uttar Pradesh. Um, I did my bachelor's from IIT Ropar in 2020. Um, and briefly after my bachelor's, I briefly worked in HPCL for around a year before joining this doctoral program. I'm currently in my fourth year. Okay. And there are contact details you can find. You can ping me if you need any help with your course as a TA. You can, or otherwise, for some journal discussion or anything. My LinkedIn or email address is available on the lecture slides, which are put up every week. So you guys can just go and um, copy the email address if you require it. Next, we'll go to the next slide. Just quickly do the recap. So last time also we did the recap of lecture one. That I will avoid today. Basically, we discussed what was the realm of gas dynamics, how high-speed flows imply compressibility effects coming in the picture, and there was some derivations that I had done, technical derivations uh, to start off with, and then we went straight to the uh, bit. Then we also answered questions of one of the students who joined last time. Um, so he had some doubts. We discussed that, and today we're going to discuss part of integral equations. And let's start with it. So let me get started. Now I'll close this uh, close this PPT and open a new one. So give me a second. Okay, let me open today's PPT. Basically, I'm gonna do it live. I'm going to write and everything live. Not much of prepared slides because you're gonna solve a problem today. Let's get started. So recap is fine. Let me just copy the PPT, the slide from the last week's PPT so that we can continue from that. Okay. I'll just share my screen also. What is this? Great. Now, so everything is fine. Share. First present here. Great. And go back. Great. I guess you can see my presentation. Um, Nobody has joined yet, so I don't know if you're all able to hear me or not, but I'll assume that you are able to hear me. Everything, I guess, is okay. You're sharing screens. That is also fine. So now let's get started. We're going to do three main problems. And let me just first dictate the problem. Basically, just recite or just say what the problem is going to be. Let me just do that. This question is from Anderson, and it's a solved problem, but still we'll discuss it in this lecture. Okay, so there is no there. This thing is a section itself. This is not a problem as such, but we'll discuss some problems on this regard. The idea is that whatever you have been solving in your just give me a second, in your video lectures, you'll see that a lot of it. Oh, we can. What is this? Oh, interesting. I didn't know this. This happens. Great. Anyways, so the idea here is fine. So the idea here is that there are some integral equations. There are some. Let me. Okay, fine. Write the integral equations first of all, so that you can start working on it. So the integral equations for mass conservation is something of this sort. Okay, let me just see if anything. So you guys can see what I'm writing. Someone has joined. Great. I have company. So someone has joined. Great. So hi Pranav. We already started the lecture, but would you like to introduce yourself? Did you before like have you attended the lecture before, or do you have any questions? Would you like to discuss something? Again,
No, sir. Um, Actually, I haven't attended any. Uh, it's my first.
it's your first year or it's the first lecture?
No. The lecture.
Okay. So maybe just because we are two in this video call. Uh, now that you are here, probably you will stay. The thing is that let me just introduce this problem which we are looking today in this lecture. This is something that we picked up from last lecture. We had briefly, very briefly, just introduced that we are going to do this time, and if you would like, basically in on now the for the next couple of minutes or maybe couple of tens of minutes, we're gonna look at this problem, thrust calculation of a jet propulsion device. See, gas dynamics is one of the major core subjects in aerodynamics, and as you know, aerodynamics is related, not uh, this aerospace engineering. Sorry, I meant aerospace engineering. Also aerodynamics. It's well, not aerodynamics. Aerospace engineering is like this. Gas dynamics is one of the major like core courses in aerospace engineering, and these problems like thrust calculation of a jet propulsion device is a what do you call bread and butter problem of aerospace engineers. And we'll do this. The whole idea of this is the integral equations derived um, in the video lectures can at least in the first instance you can solve big problems with the help of some simplifying assumption, knowing some physics of what is going on, and then using these integral equations. These integral equations have are powerful in some sense, and we're gonna demonstrate or at least see how are they powerful. Um, both integral in so okay, let me just write that as well. It may become confusing. I mean integral conservation equations. So conservation equations in their integral form have some advantages, some strengths. Just like how conservation equations in the differential form also have some advantages, some strengths. Integral conservation equations also have some certain strengths, and one of those strengths we are gonna um, uh, discuss today. Okay. If you're fine with it, if you're fine with it, I would like you to tell me the integral equations for the mass conservation, momentum conservation, and so on. So is it possible, or just the first two? Because today we are going to use, or maybe all of them. So would you like to do that, or do you want me to just write it?
Um, for the mass conservation,
Yeah,
it's
go ahead.
the I think
Good evening, sir.
integral.
Good evening, Adarsh. Hi. Yeah. Yes. I think Pranav. Yes.
So, yeah,
Yes,
yeah.
Pranav. You were telling
It's
me. Yes.
yeah, partial derivative with respect to time of integral rho dv plus its integral rho v dot dA over the
Okay.
control surface
Okay.
equals zero
So someone
for the
has to
mass
mute.
conservation.
Adarsh, I think you should. It's you, right? The sound. It's you. Adarsh, please mute yourself. I'll mute you. I'll try to mute you. Yeah, fine. Yeah, Pranav, you can go ahead. So, one
Yeah,
question is this d by dt term outside the integral or inside it, or
it's
does it
initially
not
it's
matter?
outside. Yeah, initially it's
Ah,
outside, but we can take it inside in some conditions over
how do
some time.
we? Okay, interesting. But do you guys know what is the procedure? Well, there is a formal way. There's a formal method,
I
or yeah. So
I
do
think
you know
it's
how?
I
Ah,
think it's Leibniz theorem, right?
yes,
Or
exactly,
yeah, yeah.
exactly. But it's exactly Leibniz theorem, and it's very interesting that you know that. Because generally people would say Reynolds transport theorem. I guess you would know that as well, isn't it? Or
Yes,
no?
yes,
So it's
yes.
very interesting that you know that Reynolds transport theorem and uh, this other theorem, uh, this Leibniz theorem, are related. So now something of there is a dot product that comes. So times, or I don't know, bullet, I think, yeah. So you guys can see me typing in real this. You can see the changes on the slide, right? B.
Yes, yes.
Great. And DA, right? That's the statement, right? This is the mass conservation, right? Let me write this down. Sorry, I'm gonna take this slow today. I'm not gonna. Okay, let me just check also. If we would need this. This is the primitive form. This is like just stating the conservation of mass. But how do we, like, once we apply Reynolds theorem and so on, what is the statement? Let me just check from the book. I just see. Okay, fine, fine. Then this thing, this is a conservation momentum, not conservation. Let me just check. Okay, just give me a second. Okay, right. So now it can.
Sir, I think there is one extra velocity term in the surface integral.
Let me check. So
Means
you're
you
saying something
have
is
someone
wrong, is it?
extra. There
Huh?
is one extra velocity term you have
Oh,
included.
yes, yes, you are right. You are right. That comes in the momentum equation. You are right. Yeah, big mistake. My mistake. Let me remove that. Well, if that is the case, and then this is dot product is fine. And I should not use V, I should use U because V I have used for volume. Right. So, similarly, can you tell me um, the momentum equation? Very, very, it's not even that tough. It's in fact, we can just use this one only. Let's see.
We just need to add one extra velocity term in both the
Yeah, great.
equations.
So, Pranav, this is your first time, right?
Yes, yes, yes.
Would you like to introduce yourself? Meanwhile, I check something.
Yes, I'm Pranav. I'm currently studying mechanical engineering uh, in second year. So,
Okay,
yeah, actually, I'm parallelly learning fluid mechanics. Still,
okay, and
I've actually
hmm,
I've actually done these concepts a bit beforehand, so I know a little bit about this.
amazing, amazing, amazing. Well, today we are not doing anything on. What college are you from? I didn't get that part of. Uh,
No, no, I didn't mention that. Yeah, I'm
yeah,
from Mumbai, VJTI College.
PG.
Yes,
You said Mumbai, is it?
VJTI. Yeah, from Mumbai. That's VJTI
Great.
College.
Amazing. Yeah. So one small clarification that I need to. Well, today we are not discussing Reynolds theorem, so something that we and there also has to be a change in this also. So, others, do you see a problem in the equations that we have written down?
Yes, sir.
Yeah, go ahead. What is the problem in the equations that you see? They are incorrect right now.
Uh,
So we have
sir,
has to be d by dt.
uh,
So,
it,
Pranav, one mistake that we did was because we integrate over volume. There is no space dependence anymore on this integral. It's a only time dependent integral. So now it does not make sense to have partial derivatives. Simple stuff. Anyways, let's get. So I just wanted to write this thing down. Not that we are gonna use it or anything, but the thing
sir,
is, when
sir, in mass conservation equation, B vector, what is represent? Outer
uh,
normal vector.
so V is the volume right now. So V is the
No,
volume here.
B.
Ah, B. Yeah, interesting. Okay. So this B basically is uh, well, B is the control volume. Uh, Let me think. It's actually the relative velocity with respect to control volume. But I think, let me see. Let me go to what Sir has written down.
N cap written,
Um,
sir.
N cap.
In place of B, mass
No, no, no.
conservation equation.
Okay. Okay. But that is also U relative. Then this U has to be U relative, not.
That may be
So
the normal component.
yeah, yeah. So then if it is if that is the case, if we are writing that way, so then n cap is the normal vector. Then you
Outer
write
normal.
okay. And
Hmm.
then here also we need to do this and you dot you do this exact same thing. Is this fine or am I making a mistake here? Yes,
Momentum
this is
equation, sir.
okay. Both of them. Am I making mistake in either of them?
In momentum equation, almost correct, sir.
Correct. Huh?
RHS means no surface force
Yeah,
will be
yeah. RHS
no
is not
pressure.
zero. RHS is yeah. I'll do that also. Yes,
Uh,
right. So this is integral S,
Control volume
and there are
rho
some
into F
surface
vector.
forces. Surface,
Uh,
well, right? Surface forces. Okay.
yes, sir. Rho into F.
Just a row into what?
Rho into F vector dB.
Well, So, acha, okay, you're saying there will be body forces also. Yes.
Hmm.
Okay. Agreed.
Minus P dot n cap dA
Well, no,
control surface.
no, no. Now that I have included this force, well, I
Oh,
have to write.
shear force.
Well, S. S is the surface, okay. And now that you say that there has to be a volume integral also, I'll do that also. Wait, V. What else? Yeah, rho times there will be some G. So I right now let's represent any body force in
Hmm.
terms of G. Okay, G is that body force per unit volume,
Uh,
per unit mass. Sorry. Okay.
for
Okay,
it.
G is right now here. It is not gravity. Okay, don't get confused. Or let me change it to another symbol. What symbol should I change it to? Because B I have used for that control volume velocity, local velocity of control volume. I want to use something else. Let me just clarify that. G is not gravity. Let me just write that. Okay, bar G is not gravity, but force per unit mass.
Hmm.
But oh, body force per unit mass. Okay.
Yes, sir.
Now, okay. Anyways, force per unit mass. Okay, fine. So I just told Pranav also that the idea here is that because this is a core aerospace course, um, we are going to solve a aerospace problem. Okay,
Hmm.
we are going to solve a thrust calculation problem of jet propulsion devices, and we are going to do it using integral conservation equations. That is why we were discussing these equations
Sir,
right now.
this
Mhm.
is not discussed, I think, by sir.
This has been discussed by sir, is it?
Uh, Integral equation discussed, but the thrust calculation on a jet propulsion device.
Has not been discussed, right?
Uh,
That is the intent for today. We are going to discuss
yes, sir.
this thing. In fact, the idea is not discussing this. Idea is the focus is on this, and it is just one of the applications. The idea is
Okay,
to
sir.
demonstrate to you guys that there are certain advantages of both type of equations. So partial differential equations (PDEs) again conservation equations in the PDE form have certain advantages, but integral equations, I think it's dark in here. You can't see me well. Let me just uh, leave the room. Okay, now it's better. Yeah. So, any one of you would like to tell what do you think are the advantages of? So, I am saying both of these have certain advantages, but would you like to tell me what advantages will any like each of them will have over the other? There are certain pros and there are certain cons for each of them. Uh, do you guys know what are we talking about? What
Sorry,
advantage?
what are we
Hmm.
comparing? Sorry.
We are comparing.
Hmm.
Okay, yeah, good. Let me just write that down. So we are comparing the two forms of the conservation equation. Two forms of the conservation equation. PDEs versus integral equations. And do you guys even see a point in this? Are they not equivalent? Can we even have can we even compare them? Are they not equivalent, or is there something different in these two forms of the conservation equations? Can the question? Let me ask this question: can I calculate thrust of a jet propulsion device using PDEs? What do you think? Or what do you think? How will we solve this problem? First, what are your first thoughts that are coming to your mind now that we have not discussed anything yet? What are your thoughts? What are we gonna do now? That is one. Second is, can we compare PDs? How are we going? Second question is, how are we going to solve this problem? If you would know. Third question is, uh, can we use PDs to solve this problem? And the fourth question is, I am putting a question that I'm putting a statement that we are going to solve them using integral conservation equations. So the question I'm trying to say is there are two forms of conservation equations, and are they comparable or not? I made a statement that one form has certain advantages of other, while the other form also has certain advantages on the earlier one. Do you guys philosophically think that there can be such things? Because aren't they just equivalent? That is my question, the last question. So you guys can try to answer any of these. We can move forward with those that discussion. Or if you would like not to volunteer, you can also say no, sir. You can just go ahead. Not sir, but bhaiya or anything. Shrey, you can call me by my name. Yeah. So you guys can just um, unmute yourself or say anything. No?
No, actually, can't think of anything.
Sir,
Ha.
this integral equation is convenient as compared to PD.
It is confident.
Convenient to use OD or integral equations than PD, partial differential equation.
Are you sure?
Yes, sir.
But why do you say so? Why do you say that they're convenient? You're saying convenient, right?
Uh,
But why?
and because integral form total averaging type, in differential form element wise.
Interesting. So that is the crux of it, Pranav. Have slightly have today, and that is the whole point of today's presentation. That sometimes in certain problems, even though they are equivalent in certain problems, solving solving the problem using one form is more convenient to the other, um, because of certain properties these forms have. You see, once you integrate over some volume, you lose the essence of you can't resolve anymore. You can't resolve what are the internal details of the problem, or whatever the quantity you are solving for. You can't figure out what is the internal distribution of that quantity. So okay, suppose if I want to calculate um, pressure variation across a pipe. If I know that del P by del X equals to a constant, I would know that the pressure varies linearly. But if I just tell you, now that you know that pressure varies linearly, if we don't use that information, and I just tell you that the pressure at the inlet of the pipe is something, pressure at the outlet of the pipe is something, can you guys tell me what will be the pressure variation across the pipe? Unless it is given, unless you know that it is linear, you can't say anything, right? This distribution, local variation of how pressure is changing from the inlet to the outlet is something that is coming from PDE. We say del P by del X is a constant, right? You guys get that, right? But if we integrate that equation, what exactly are we gonna get? We're gonna get that delta P is some quantity which is a function of length, right? Delta P is some quantity, something times the length. Okay. And you can't figure out if it is a, unless you know that del P by del X is a constant, you can't say how will your pressure profile vary. It can happen that the same thing. So basically what I'm saying is, suppose there's a long pipe. Okay. Suppose there's this long pipe. This is the inlet. I'm not gonna waste some time on just drawing this. Let me just quickly do this. This is the inlet, this is the outlet. Okay. And we know that, well, let me come here. And so this is the pressure P inlet, this is the pressure outlet. If we integrate over this pipe, we are going to know only these 2 points, right? That this is one point at the inlet, and at the outlet, something of this point will be there. Now anything can fit in between these 2 points. It could be like this or something else. You get my point, right? You guys just tell me if you agree or disagree. That is all I am expecting right now.
Yes, yes, sir. Yes, sir.
Right. So that's the whole point. So that is the weakness of integral equations, that you can't resolve the internal details of your solved quantity or anything. But at the same time, if you don't need only, if that is not the purpose of your analysis, you don't mind not knowing these details, then think about it. This becomes this apparent weakness just becomes the strength. You don't see, uh, calculating internal details or even computing and saving these internal details will become computationally expensive because you have to store a lot of information. Now that this was a one-dimensional problem was fine, but if I give you a three-dimensional problem, you have to store so much data. At every point you need some quantity, which does not make sense. If integral equations are good when you don't require internal uh, details, okay, and that suddenly becomes the strength, and that is exactly why thrust calculation was chosen as a problem to demonstrate this strength of integral equations. We'll see for a jet propulsion device, the internal details are pretty much complex. But once this averaging out, which I think, sorry, I'm missing your names. Yeah, Adarsh mentioned, this averaging out you'll see that these basically when you calculate thrust, you're integrating over the force which is applied on every section of your engine, right, by the air. The whole point is that you have an aircraft. Air is flowing through that through its engines. That is it, right? So any force that you're generating will come only from the fluid that is uh, what do you call it? It's covering this engine or whatever, right? In immediate contact of this engine or aircraft, that only that fluid can apply force, and that is how that force has to, like, if the plane is flying, then we would know, we will have to whatever force this airplane is getting to move forward must be applied by this fluid, right? Simply Newton's third law. So that is the whole point of it, right? So I guess I made some sense. Anyways, so we'll start. Okay. Now there's a catch to it. Suddenly when I'll solve this problem, and this problem gets solved, and we'll get to an answer, you'll think that these integral equations were very powerful, that we were able to solve a very complex problem to get a very simple answer. We'll get a very simple, very nice, clean answer. But let me tell you, through the course of this example that we're going to do, it's not only the integral conservation equations that we are going to use. We are going to use major simplifications that help us. We are not going to get very clean. We're not going to get very clean um, what answers unless we use heavy simplifying assumptions. And in that sense, even a PDE could help you, because the whole point is simplifying assumptions are the hero here. Okay, they help you a lot. So we'll see, we'll get stuck at a lot of places once we are into solving this problem, and simplifying assumptions will come to our rescue. So let me move next. Let me see what all do we need to discuss. Okay, what else do I have? Hmm, how do I start this problem? Okay. Um, okay. So maybe just quickly I can go through this principle also, that suppose there is a balloon. See the whole point, how what is the whole principle of this jet propulsion is. That would also be a good discussion that we can have. So suppose there is this balloon, right? It's not tied. Okay. Now we know that inside there will be some pressure. That is why uh, it is in this inflated mode, and this pressure will be equal, right, to the atmospheric pressure. Isn't that correct? Now the thing is, once it is open, this it's inflated and it's not closed and it's open. We can treat it, excuse my drawing skills. Yeah. Now again, we know that the pressure inside is gonna decrease because there will be some efflux of mass. But the pressure at this opening will be again something close to what? P infinity or P naught, this pressure, right? And
Yes, yes.
right, and on this end, well, this is incorrect. That is not going to happen. So there will be some pressure. Let me just remove. Let me just erase that. I made a wrong statement. There will be some pressure. We don't know that pressure yet. Okay, some pressure. And roughly speaking, I'm just roughly speaking here. It's not accurate. If we apply the Bernoulli equation at this point, we know that p plus half some velocity had is some constant, right? Which may be, let's say, p infinity, because here velocity is zero. So maybe we can relate by applying Bernoulli. We know that this pressure will be lesser than this pressure. So p is less than p infinity, or what the hell? So no, I'm making some error. So what do you think? What I'm where am I going wrong here? I'm saying something wrong. What do you guys think?
The the inner pressure should be greater, right? Greater than the outer pressure, so as to propel it.
Ah, yes, it should. No, it should be greater than what you're saying. Let me go back to the slide. Yeah, so it should be greater. This is greater. Fine, that is okay. So some p inside pi is higher than pi is higher than p infinity. You're saying. Oh yes, oh yes. That otherwise it will be a non-inflated or something. If it's inside it's lower, then it will be, yes. Let me think. Yeah, because there will be tension also, that which just didn't, I just ignored. Because there will be tension on the balloon also. So the pressure inside will be higher. Agreed. Now what? Now what? So this pressure will be higher. Okay. And what? Okay. So maybe we can't just deal by this because
So
hmm,
the half v square, half
hmm.
rho v square, that term I think that should come on the right side at least, because the inner static pressure when it gets out, it will it will drop down to P infinity, and some of its part, the excess part, would get converted into dynamic pressure.
Wait, let's do that. So you're
Mm,
saying, you're saying, okay, you're saying pi should be equal to,
yeah, P I equal P infinity plus half rho v square.
yeah, that makes sense. Great. That makes sense. Let me just clean this up also. Array, what happened? Controls. Oh, I can't do. Oh, I erased all of it. No problem. Yeah, well, that is the whole point. Let me erase it all. So now we have this balloon, and there is this pressure inside, right? This pressure, why is this pressure higher inside and outside? So basically, we are saying that Pi will be higher than P infinity. Why? Can you tell, Pranav?
Yeah, means the inside pressure for it to inflate, there is this tension in the balloon, plus
Yes. Yes. So
yeah,
if we
the
locally
tension
solve,
force.
yeah,
Yes.
so if we locally solve this, there will be a tension force, something 2 pi RT or something, plus Pi, some plus P infinity will be equal to Pi. And again, we have to do this also. I think if I take theta here, so then we have to do what? Sine theta, something of that sort. If we solve
Yeah,
this,
yes, yes.
uh, something of that sort, then we'll see that Pi is greater than P infinity. Fine. Now, this is the pressure that we are getting, P infinity. Pi, sorry. Uh, the force outside here, it's P infinity. On this end, what is going to happen in this open this opening where the pressure is flowing? What is the static pressure here? Here.
As soon as it gets out, the pressure drops down to the outside P infinity pressure. So that excess pressure would get converted to half rho V square.
But what that is fine. Okay, that is fine. But let's say if I were to put a pressure sensor just at this place by some magic, what would it measure? Will it measure P infinity or will it measure Pi or what? You said it, right? You said it. You said it correctly. That because the pressure has to drop. Well, again, then this
But
becomes a little tricky
the
in a jet in a jet also. When we have a jet in a tank or something, the pressure does not instantaneously becomes equal to infinity,
yes,
but
it,
for the loose sense of it, we can say that it is roughly equal to P infinity. Let's say it's roughly equal to P infinity. So now we will see that if we were to solve the pressure forces and on the entire of the balloon, we'll see that the pressure on if this all every let me again remove this. Uh, this balloon is there. Now, if we were to solve everywhere except in this region, we'll see that all pressure forces will get cancelled out because of the symmetry of the balloon. Although it does not look symmetrical, we see that pressure here will be P infinity, and here it's Pi, right? Well, if you think about it, there is no pressure on the balloon in this region. The P infinity is the static pressure, but the force on the pressure on the balloon itself is there is no balloon in this region, right? There's no balloon in this region. That is why there is a hole, right? So there's only force on this edge of it, this edge of it, and that is Pi minus P infinity. Why Pi minus P infinity? Because Pi in this direction and P infinity in this direction. You get my point, right? There is no force on this region. Oh, fine. There is a static pressure here, but there is no balloon in this region because that is why there is a hole. So we are calculating for we can calculate the force on the balloon and see that there is a net force on the positive direction. That is why it moves forward. That was the whole point. I was trying to just imply that uh, philosophically, jet propulsion device also works on this principle that we get some excess pressure in some direction. So there are pressure forces, and we'll see there are other components also. We'll see one by one. Okay. I think I kind of solved, kind of closed what I started this discussion. Is that okay, or did I leave things untied? Just some feedback, maybe. Is that okay?
yes, you. Okay.
Okay, fine. So now the task we have, similarly, the tasks right now that we have is to do this. Okay, I have to copy it there. So the task, okay. What is the brute force method of solving the problem of this problem, the thrust calculation problem, the force we want to calculate on the plane, let's say. Wait, no, this is lecture 2. Let me close this. Close this. Just give me a second. I will come back. Mhm. Yeah, lecture 3. Right. So what is the brute force way? Okay, this is what I was trying to come at. The brute force way would be to integrate the force applied the on the body of the engine or this duct or whatever and integrate it over the whole area. That is how we calculate force, right? That is what we did on the balloon also. We can calculate it across the entire thing. We said in part of it will get cancelled, and in some part of it we saw that there is some net force on either side, and that is what we are going to do. Similarly, we are going to see that there is now in a jet propulsion engine, in the balloon there was only an exit of the flow, just like a rocket. We'll see a rocket is very similar to a balloon. There's only expulsion that is happening of air and some combustion byproducts. But in a jet engine, there is an inflow also and there is an outflow also. So there are two holes now. Okay. And what we are going to do is solve this pressure excess problem and see what is the net force you're going to get. Okay, that is the intent. Now, how does this look? So there is again, just like in the case of the balloon, there was some cancelling out, which I just didn't discuss that what cancellation I meant, but we'll discuss it in this case. So let me again, I'm just basically what do you call taking screenshots from this book, which I'm using to explain this problem. Wait. So now, selected book. I have to close this first of all. I don't need this. Hmm, that's okay. So what is this now? Let's discuss. Okay. So guys, do you know that the pressure force is somehow related to the projected area of any body? So let me just do that also. Please. This is some basic stuff. Again, very stupid of me to discuss that. But the thing is that you gradually move to the solution rather than simply stating facts. I want to gradually move to the solution so that it becomes clear to you every time. We recall a lot of steps also. The point here I'm trying to make is suppose there's a beaker and there is this is a water beaker and we are trying to calculate force on this edge of it. Okay, so there will be some pressure and assume this pressure is a constant pressure. It is not very largely. The height difference is not large. So this rho gh term, the term that barotropic term that will come is negligible, let's say. So you have only pi. Can you guys tell me what this net force will be in the two directions? So the idea is similar. I'll just go ahead and I think it's very straightforward. If you solve this, the pressure force will always have two components, a horizontal component and a vertical component. And the word horizontal component, if so, basically, if I try to write the force, I'm writing pi, uh, this angle, whatever angle I'm going, pi, and then this area. So I write this area. Let's say this area is A. Let's say A. Okay. A, and then the angle which I have, maybe sine theta or something. And then there will be again pi a cos theta, the other component. Let's say uh, this is the horizontal component. Let's say this is the vertical component of the force. If we put it force, df. Am I doing it very uncleanly? Please tell me if that is the case. I just want to quickly move to that point. Don't want to waste too much time here. But anyways, so del dfx and dfy, right? Do you guys agree? And then we have to integrate it both sides to get fx and fy, right? If we just
Yes.
simply, right, that makes sense. So now just a simple thing, and we can see that pressure acts on the projected area. We'll just see that. The beauty is that pressure always acts at a normal to the local area vector always, and that causes it to always have a what do you call um this projected area things come. So now I wrote force. This is the force, local force, but you just recombine this. Okay, earlier it was pi a into sine theta. Now you say pi into a sine theta, and they are just equivalent. So now you will see that if this was the area that we were looking at, this thing is this. You'll see a sine theta will be this x projection of a on the y axis. This will be A sine theta. And let me call this as AX. Similarly, this part will be A cos theta. And this is AY. You get my point, right? We just do this recombination. It's two looking at the same thing in two ways. So what basically the point here is, let me just erase things. The whole point again is that if I have to solve this pressure problem of this beaker, which I said, I can just simply say the force exerted on this beaker in the x direction will be equal to this pi into this height, let's say h, and it will be just pi into h into whatever lateral length it will have. Okay, let's say if this beaker is of some direction, and whatever the length is b, or some volume. The point is that this rho pi, it's very dirty, no? Let me just write it properly. If I'm writing, then I should do it properly. So pi, this h, and then some lateral volume, lateral length scale. Okay, this will be fx. Without solving anything, we can write it. Okay, because this is the projected area of this surface in the x direction. You understand that, right? Projected area. What do I mean? The this surface
Yes,
has a
yes.
if you look from from the perspective of x-axis, this is the area. This is the amount of area that you're going to see. Okay, and if this is the case, then you will have L into V, where L can be this length scale. Okay. So similarly, we can first of all look at the pressure forces uh, on this duct. Okay, now one more thing which I did not discuss right now is the fact that effectively engine can be treated as a duct. Okay, that is the first order if first order effect of an engine. I told you, right? The simplest the simplest representation of an engine could be simply a duct. We see that um, and that is coming from the experience of aerodynamists. Okay, the fact that this can be modeled as a duct is something that will come by when you solve the more complex problem. You see that if we treat the engine as a duct, we solve the problem, the answer we will get is close to the actual value. Then we can say, oh fine, our assumption was fine, we are not missing some first order effect, we are not missing some big effect. Okay, so the fact that this duct thing has been taken care of is something that we won't know as students, first timers. But because we are solving this problem, I'm giving it to you that we can take this engine, because engine will have a lot of things going on, right? But the whole point, again, the integral equation, the whole point of the integral equation is that we don't need to take care of the internal details. And we saw that if we solve this problem in this simplified manner, we see that the answer that we get is quite accurate. So anyways, the net force acted on this duct, and this variable area duct or something, you see it has a shape of similar shape to a air engine, right? Compressor, turbine, all that, propulsion engine, right? You've seen that, right? Let me see if I have image for it. I guess not. Yeah. So
Yes,
this is what I
yes.
meant. I guess this is what I meant. So we have a compressor here, then there's a combustor, and then it expands in a turbine and nozzle, and then it leaves. So that is okay. Now the net force. Earlier also I did a net force, Pi minus P infinity. If you do this, you'll see that the inlet, and that is a characteristics of gas turbine engines, that the inlet will be have a higher cross section, the exit will be a lower cross sectional, will have a lower cross section area, and the net area, the net projected area in the x direction, because we are interested in calculating thrust, we are not interested in calculating the lift of the jet propulsion device. Now tell me guys, any one of you, can we calculate lift using this geometry? So already we have made some certain assumptions and some implicit assumptions that we have not, although we have not formally started the analysis. I'm discussing some weird way the problem, but there are certain things that let's address them. So first of all, in a airplane, thrust is generated by the action of this propulsion device or in an engine. You know that engines in a airplane are solely for the purpose of thrust. Okay, the plane will move because of this thrust action. What is the component by which the plane flies? Is it the engine? That is my question. When I say that, then can we calculate the lift using this geometry? I'm asking, can we calculate the lift using this control volume of this um, engine, this duct?
We don't get the lift from this thing. We need the wing structure and the airfoil. Like that
Yeah.
structure for calculating lift.
Right.
But we can
So the
get
thing
thrust
is,
from this. So we can
hmm, hmm. Yeah, so that is the whole point. That thrust we can calculate from engine, but lift is majorly generated by the plane wings. It might have some, well, this is a symmetric problem, so we'll see that it is, in this case there will be zero lift. But suppose there is some asymmetry, even then, the amount of lift this could generate, possibly generate, potentially generate, would be low, and majorly plane generates lifts using wings and not this propulsion device. This is basically for jet, this thrust generation. Okay. Now the second thing is, there's an important force that I am missing here. I am not mentioning also. Technically speaking, precisely speaking, I should mention one force which I'm missing, which is required when well, is pressure the only force that this engine is gonna experience, or this duct gonna experience? There's another force which we are not considering right now. And why not? Maybe any one of you. I guess we are two. Oh, we are only one. Yeah, Pranav is only there. Hmm. So Pranav, one force
yeah.
that we are missing is the shear force. And do you think there is a good reason to ignore it?
Because most of the things which we would deal with are the normal components, right? The pressure forces, and they're
But
more
hmm,
significant right now. The shear
but
force
don't you
would
think
actually
that would do what?
it would contribute to the drag effect, the
Right.
resistance.
But amazing. So it will contribute to drag, and it will not calculate. It will not. If we were to be calculating net force, then maybe you could have thought about this. You are correct. The thought process is at the right place. So you're fine. But the only point I want to add to this is, again, the wings will be the major contributor to drag of the plane. Even if we were to consider drag to be something, um, the drag over the wings will be much larger. But again, why? Because wings will have larger area. That is how they generate lift, right? We have big, a lot bigger wings than the size of the turbine. Okay, or the whatever this thing is called, jet propulsion device. Okay, let me check one more thing which I wanted to point out. I must have written it down here. Yeah. So as you said correctly, there is one big thing, that pressure creates thrust. The normal components. You said the normal components are the major contributors to thrust, and that is the case there. Okay. I jot down. Okay, fine. So let me just first write the first expression to this. Okay. Now what is this thing there? So I think you guys can see my screen. Do you see the T there written down there? Probably
Yes,
not.
yes.
Yeah, you see it, right? Fine. So T equals to, we do that integration that we always want, like we would have to do. But we'll see that we'll without solving this. This is the whole point of this demonstration is that without solving this integration, explicitly solving this integration, we can just solve it rather than um, solving the integral itself. We can substitute for this integral and get the value that we need. Okay. Then we're going to write ds, or let me just use dA right now. And there will be again x component, y component. Let me not write that. And what else? IDA minus maybe, right? Minus, right? Similar to the balloon case. You can also give me feedback if I'm going very slow. Should I should I be faster? Okay, this is something that we have to calculate.
Maybe a little
Hmm.
bit. I
Ah,
don't
okay.
know much. You can.
Okay. Fine.
Hmm.
Fine. Okay. So let's go ahead faster. Um. Fine. And let me just see what have I written down here. I'm also missing a page. Like that. Yeah. This is the one. Okay, this is the other one. Fine. Let's go ahead. Now we'll quickly do it. So there's the force that you want to calculate, and uh, yeah, there's some simplifications that we can make here. So can you do you see some simplification right there in this integration? Uh, can we further expand this integration, or we are done with it?
Uh, no,
Can we do something
I
about the
think
p
we
infinity
can.
term? Hmm.
Uh,
The- Can we do something about the p infinity term?
I don't think. I think that bracket would remain constant, but the area we can
Ah,
directly
you're
integrate
saying
it to the
pi
area,
minus p
right?
infinity will remain a constant. Ah, you're saying
Yes, means
this will
according
come
to the
out.
control volume. Yes,
Ah,
like
but I never said that pi is a constant. Oh, why is this happening?
then
Uh, I never said that
yeah,
p
I
I.
think
So the thing is that no, if we
so
huh. Hmm.
during the uh,
See what you're
I
trying to
think
do is hmm, hmm. See again, I'll go back to
the
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 previous. Hmm.
sorry,
You're
it's
trying
the
to say
audio
something.
delay. Mhm.
Ah, I
No,
see.
just
Sorry.
it's just that I think at last we get pi into the differential area. I think
Okay, let
it
me.
means
Yeah.
after solving.
Ah, you're saying p infinity will get cancelled out. This is what you're going to get.
Yeah,
Is that what you're
yes,
saying? Well, no, there will be some term
yes,
that we have
maybe.
missed. Okay, so fine. Let's divide this. We had this. So at least we can write this down there. Okay, and now that we know that this outer geometry we know, inner geometry maybe not. Outer geometry we know that there is a symmetry, certain symmetry of it. So we know that certain things will cancel out, isn't it? Certain things are gonna cancel out. Okay, now you see, if
Yes,
we
yes.
were to right now, basically we are solving. I'll have to go back here. Okay, so right now we are solving this integral over this integral. I'm talking about this integral over these lines. Okay, we know one more thing, that integral over this entire dotted boundary, the dotted boundary you see of p infinity will be 0, right? So let me write that.
Yes.
So we know that something is zero and we want, see, these areas we know, right? These areas we know, right? So what do we know? Let me just write that down. Yeah. So we know something. We know P infinity into AI minus P infinity, mhm, AE, or no, yeah, exit area plus, will it be plus or minus? We have to see. Will be zero, right? Because over the whole thing, this will be zero, right? Now you tell me, there is this sign fine or wrong? That we will have to check. So P infinity AI is positive in the direction of x-axis, right? Right? And P infinity AE is in the
Yes,
direction of negative. This whole
negative.
integral, what direction will this be? This whole this integral. Let me, yeah, come here. Erase this part. The in, mhm, this integral. What net direction are we gonna have over this when we integrate it over these two surfaces? Although this is one surface, we can't see it in this 2D image. This is circular, right? Cylindrical. So the net direction you see, because I is greater than AE, we see the net force is gonna be in this direction. And opposite to the, like, in the negative x direction. That is why I've written down this thing. So this will be plus, right? Let me think. I guess yes. So this is fine. Okay. So now you get it why I wrote it as uh, see, the net force,
Yes, yes,
this
yes,
net
yes.
force is in positive x direction. Then this has to be in the negative x direction to be to sum it up and get to zero, right? So then this becomes,
Yes, yes, yes.
yeah, fine. So this is
Mm,
all.
it is-
There's a lot of bookkeeping that we have to do, because suddenly we'll see that we made a mistake. That is why I'm also going a little slow. I don't want to make mistakes. There's a lot of bookkeeping that we'll have to do. So this is something that we'll just simply substitute. Okay. So let's just substitute this part. So t equals to this. Um, and basically, now let me just check if I made the mistake. I'll check from the expression I have. Still missing a page, it seems. Fine. Now, to solve, okay, so this much part is done. So outside P infinity is resolved. Now we are going to resolve this using the fluid mechanics, the integral equations. This is where the integral equations are going to come. Let me just quickly check if I have written the expression correctly or not. So AI minus, yeah, fine. It is fine. Great. You guys, you know why this minus negative sign is coming?
for the whole integral,
This whole square bracket.
think that's
This, see, this negative you would understand, because Pi and P infinity are in the opposite directions. Why is this negative there? Why did I write this negative there?
think that's action reaction.
Um,
Uh, or I think that's uh
I'll tell you.
the, a-
It's a
the
simple,
area vector.
not area vector. The thing is, we kind of know that Pi will be greater than P infinity, right? Kind of intuitively know. Maybe not. Then we'll get right. Suppose I'm saying that Pi is greater than P infinity. So we know that this is a positive quantity, right? But T infinity, T I know is gonna be a uh, negative vector in the negative direction. The thrust is gonna act in the this direction, right? That is why it will move in the negative x direction. This engine see this engine, oh wait, this is the problem with this presentation. See, this engine is moving in this direction, right? So we know the net force will have to be in this direction. Kind of expecting this square bracket term to be positive. Wait. This square bracket term to be is going on. Square bracket term to be positive. Okay, the quantity. Something will come in the positive direction because we are expecting pi to be greater than p infinity. That is why we have substituted a minus sign so that we get a positive quantity in the negative expression. It's again a lot of bookkeeping that is why I was um, conscious about it, but it does not matter. At the end of it, it does not matter if you take it if you're consistent, then it is all okay. Okay, fine. Now we'll solve the something is going wrong with my computer. Wait, just give it a second. Just oh fine. Think it is better now. Oh yeah. Why is it here? This. So also I don't need. Right. Then what do I need? Okay. This much is done. Now let's write the conservation equation to solve this. Acha, okay, fine. One another assumption that we will need from let's put this back there. Okay, now the approach, the methodology or the approach is gonna be to use the methodology is gonna be to use this force on the fluid will be opposite of the force on the duct. That is the logic, right? We're going to apply when we're going to apply this conservation equation, we are not going to apply it on the we're going to apply it on fluid, right? So the idea is to get the net force on the fluid and then reverse its direction and to get it this pi infinity will be substituted there, right? That is the idea there. So one thing is that the conditions are steady. That is something that we will assume first. That is like one of the primary assumptions. Okay. Then the next assumption comes when we say that the shear is gonna be zero. Only in that case where we can write that the surface force can be written as minus P. You agree, right? Minus P dA, where dA is a vector, I guess. P n cap, or maybe let me write n cap. You're able to see the screen. I don't know. Right? Yeah.
Yes, yes.
So this is cap at I guess. Right? Now, this is something that we have written. What else? Okay, one more thing. Uh, this now let's come back. So basically, now that we come back, now you see that this problem or the book, the way this problem was given in the book was we've kind of treated this jet engine as steady and the fluid moving through it, right? Right? The fluid is moving through it and not the jet engine moving. So you see that the control volume in some sense is fixed. It's not moving. It's a stationary control volume. So we can remove this B stuff also, right? Fine. So this will get us what P infinity, this PI DSA. This is our intent. Okay. And whatever this PI DSA will be, oh, so I was saying that this see from this is the term of pi, so let me write pi also, and this is the force applied on the fluid. This is the fluid force. Let me write this down. On fluid, right? This term is on engine or on solid, let's say. And we know that on solid is a negative of on fluid. Okay. So simple stuff then, I guess. Couple of assumptions now. Let's go back. So again, now we need to know some assumptions about, okay, basically, rather than solving this, we're gonna solve this. That is the whole point of this problem, not something very sophisticated. So you see, one thing that we know is because there is no fluid leaving on this, like on these boundaries, we kind of know that this is gonna be zero, right? There is no efflux through these boundaries. These are like walls. So we basically want to solve the integral on these two walls. That's it. And then we can substitute it by substitute that expression there. Um, but there is a catch here. One more thing which I've missed. We'll go back. I'm doing it a little bit, what do you call it? In a very unorganized manner. But I guess you're getting it, I guess. If you have any doubt or anything, you can just let me know if I'm making something unclear. And let me just, yeah. This is not PI. Let me write this as P. Okay, on fluid. Now, this on fluid term will separate into two. It will separate into PI plus also on the edges. Also, there will be, wait, this will be some P on inlet and outlet. Let me write that. You get that, right? Or let's not write this here. You do you get this equation that I have written down? Does this make sense?
Yes, yes, yes,
Makes
yes.
sense, fine. And now we will, so to figure this one out, we need to know two things. We need to know this. Oh, you can't see the highlighted section. Fine. So you need to know this part, and you also need to know this part to figure out this stuff. Okay. So now let's move ahead. Now again, couple of now we are stuck. It's if you see um tech, objectively speaking, integral equations are not helping us anymore. This is it. They have just there are just substitutions that we have made. Simplifying assumptions are gonna come to like come for rescue of us to figure this out. We have some simplifying assumptions to substitute in here. Okay, so first assumption is that we kind of know the pressures here. See, at the inlet, we can expect the pressure to be P infinity. Okay, do you get that? By the pressure
Yes,
at the
yes.
inlet, you get that, and equally the pressure will also be infinity at the edge, right? At the exit. What will happen on the exit? P infinity only, no?
Uh, yes, 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 yes. It would be
No.
P infinity, but that
Hmm.
Pi is we are actually increasing the pressure in the interior, right?
Yeah, but at
So
the edge, what will happen? This pressure, what will be this pressure? You
at
said
the
something about
edge,
Bernoulli equation.
on the-
Hmm.
on the left, it would be Pi, but on the
PE.
right
You're saying
at
on the left, it will be PI. On the
means
left, is it?
Left means inside. I mean,
Not inside.
it's getting.
We're not. So we are basically now right now. So again, now let me go back to. So see, the plan of the thing is that this part of the integral, we see on the fluid when we solve this part of it will get. We have to solve it on the entire of it, right? This is we have to decide a control volume, right? We have to decide the control volume, and that control volume has to be closed. It cannot be an open control volume. So now that surface can be broken into two parts: the edges or the inlet or the outlet, and the body of this engine, right? So this part, yes, see this entire thing has this surface. Excuse my drawing, I've drawn it very badly, but it has all four edges. This one is just this. This one is this, and this and this. You get my point? Or again, I have to do it properly.
Ha. Yes,
You
yes.
get it?
Got it. Yeah.
So now the intent here is, because we can't calculate, we don't want to calculate this part. This part, we're going to make some statements about this one, and also this term. This term. If we know this term and this term, we don't need to solve this term. That is the whole utility of the this integral equation or the conservation equation. That is the whole intent, first of all. Okay. So now, so first of all, that is the intent. Now my question is, in our attempt to solve the pressure integrals on the edges, I need some assumptions. I'm saying upfront that we would need some assumptions, but I'm asking you, what are your views on the pressure values on these two edges, at the exit and at the inlet? What do you think?
The inlet,
What will be the
it would be P infinity.
where
It
inlet?
inlet.
It will be P infinity, you say. And what
Yes.
about this one? Let's say PE. Will it be equal to P infinity? That is the question. And if not, why? Sorry for that bad handwriting. Why
Uh,
not? And
it
why
would
is this?
actually
Okay,
dip
let me put another question, and you answer both. Why is this P infinity? Why? Let's ask this question first.
because
Why is it P?
it's
Yeah.
that is a incoming fluid, so
Hmm.
that inherently it's having P infinity pressure. Like we are assuming it to be uniform. So
Are
just
we
before it
assuming it, or
enters, or
we
just
know if no? Are we assuming it to be P infinity,
no,
or
no,
we
we
know that it
assuming
is
it
P?
to be uniform. We know it is P
Uniform is
infinity, but you're assuming it to be uniform. Yeah.
okay. You're assuming it to be a uniform, but we know that the value is going to be P infinity. And you're saying that is
Yes, yes,
because that's the incoming flow, and the static pressure is
yes,
away from the engine is P infinity, so it will be P infinity.
yes. It
Good.
hasn't
That is the
entered the
exact answer.
engine. So yes.
So now you're expecting it to be not equal to P infinity. But can you reason why it is not P infinity?
Because after
See, your
compression, it uh, it
but do you
may
know you
expand in. So sorry,
it will okay, yeah, good. So you said something about expanding. So now you have some
expansion. Yeah.
intuition. Yeah, so you
Yes.
have some intuition that you expect the pressure to go down, not immediately, but slowly. This will be some PI, and this will be P infinity again. Okay, so you're correct in that way. But the thing is, not everyone has that intuition, and it becomes a little bit confusing why PI will take so much time that we can't treat it equal to P infinity. That is something not everyone will get. That was my intent to pose this question. The thing is, from experience, or maybe in some way, that the jet which is leaving the engine is fast enough so that the pressure there cannot be treated equal to P infinity. I also don't know if it is higher or lower. Maybe it can also be lower. I don't know. It will be actually lower. It will not be higher.
Yeah,
It will not
mostly it
be
is lower.
lower. It will not be higher. The point was that it will asymptotically go and meet P infinity after some time. That is the property of the jet, right? You mentioned something about the Bernoulli also, and we can see that happening. So, anyways, let's go back. Simple stuff. Let's just put all things in the equations and let's get on with it. Let me erase everything before I start writing. Yeah, good. Mhm. Okay. So now what we know is that this on fluid term is equal to what? Uh, Now I'm gonna write this integral. Let me just color it so that you know what I'm writing right now. This term, the pink term, I'm gonna write the expression for it. Okay, so this will be equal to rho rho infinity, or let's say, yeah, let me write rho infinity and v infinity square, right? AI and minus. Will it be minus or plus? It will be This will be minus and that will be plus. You have to tell me why. The rho E. This will be BE. You have
It's
to tell
because of
me
the minus sign we took
what?
previously.
What? I didn't get
No,
that.
no, for the integral, for the integral, we
Yeah.
took minus pi into, so it, uh, so taking a minus, taking a negative of then integral, actually it would be exit minus inlet. So, no,
No,
no, wait,
no.
no, 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 no,
Yeah.
no.
Got it.
It would
No,
be
no, no.
inlet.
Take your time. Take your own time. Yeah. And what else? This term.
No, no,
Now the
sorry,
other
it got
term is gonna
confusing.
be. No, it's okay. Take your time. Just that I want you to think about it. That's it. There's no right or wrong answer. Even I'm getting confused multiple times. That's okay. So this one is okay, fine. Yeah, maybe right this part here. Yeah. So let me know if you have some answer. Like if you're able to think about, like if you're able to make progress. I'll tell you why. It's pretty simple. See, there let's wait for you to come back. What is this gonna be? This is gonna be. You're there, right?
There should be a plus sign, right? On
It would be
in
nice
this
if you
previous,
point out any fallacy in the equations. Yeah.
no, no, in the previous equation, after the
Huh.
square brackets, it should be plus sign, right?
So see the let me this is term. Okay, you can't see this. Let me color all the terms. Okay, let me color this term also. Color all terms. This should be some other color. Can't see this. Oh, yeah, this is fine. This is also purple. This is also gray. Now, fine. This term is blue, right? See, pink term is equals to gray term, right? Right? Now I am substituting for the gray term. I wrote that it is gonna break up into two. So the gray term breaks into blue plus yellow, right? Blue term will be gray term minus yellow term. Correct? Correct?
Yes.
This
Yes.
term is the pink term. Now tell me if anything is wrong. Is this minus wrong?
No, no, sorry, sorry.
Basically,
Still got confused.
you got my
I
point,
got
right?
confused. Yes, yes.
Uh,
Didn't see that.
the way I'm telling is not proper. It's not proper. But the thing is that online it becomes difficult because I have to write it multiple places. If I had a board or something, I could have done it properly. But I guess it's not that big a thing. These plus minus is okay. Anyways, I will continue. You tell me why this is VE minus VI. Wait, AI. So it's AE minus AI. You have to tell me that. Meanwhile, I'm writing the yellow term. I'm expanding the yellow term. Okay. The correct way to do everything is write it vectorially. If we have to do it, if I had to do it properly, everything properly, I would have written I cap and J cap and all those things, so that there is no issues of directionality and other things. Right now, because we are mixing things, right? We are mixing minus signs with X direction, Y direction. It's becoming difficult. Otherwise, if you want to do it properly without getting confused, the ideal way to do it is mention I vector J vector, so that you don't have to do any mental calculation. Whatever is there will come out naturally. If it is a negative quantity, it will come. If it is a negative positive quantity in negative x direction, it will come minus I cap. So that is fine. Okay, I think it's fine only. Uh, See, why are we getting AE minus AI? It's basically because of
Uh,
that
uh,
n cap vector. Okay, the velocity is in the direction of outward normal or at the exit. It's in the negative opposite direction to the outward normal in the inlet. That is why I have written minus. You get that now?
okay, okay. Yeah, yeah, yeah. Yes, yes. Okay, okay.
Is that okay?
Okay, so
Similarly, I
if the
wrote,
A is in the direction of N cap and AI is in the okay in the opposite
yeah,
direction.
we kind of treat it as like n cap is always outward to the surface. And now that we are solving it for the fluid, so for the fluid, n cap has to be out. Like, so wait. Yeah, here only. So this will be n cap here and n cap there. So this now it's okay, right? With this, velocity will be in the direction of n
Yes.
cap. So this term will be positive. Yeah, fine. Similarly, here also, although I've written minus p, but you note minus p is kind of implying the force on the body. Minus p means in the negative direction of n cap. So I can actually remove n cap here if I do it properly. Minus means that it is in the direction of negative of outward normal. So in that case, that is why this AI is coming positive, because it is in the pressure is in the direction of wait. So wait. I have to look things. So again, let's see. What is the time? Okay. Mm, so this is P infinity and AI will be in this direction. So yes, we will have to do it other way around. So maybe I can write it here. This minus sign is this equal, right? This I think makes sense. Again, one more thing, if we do the conservation equation, can I write this? Now you tell me. Uh, you seem like a smart guy. You tell me this thing. Can I write this? Simple stuff only, not even like stupid stuff only. You tell me this. Can we write this?
Um,
So,
hmm, okay,
right?
so rho v into is it
Mass conservation.
are
Ah,
you
okay, yeah.
trying
Oh,
momentum
AE also will be
conservation?
there. Yeah,
Ah,
AE
okay,
also.
okay, yeah, that's um,
Now can we write?
so rho into yeah, we can actually uh, mm, I rho ve it's the inlet and these are actually the these rho into v that's mass. Yes, we can write. Yes,
We can write.
yes.
You told me you can write. So there's just small thing which I wanted to just point out. Again, not a big thing, but it's roughly equal to, because in a real engine, the thing is that there is also mass addition that happens inside the engine.
Yes, yes,
You
the
add a little bit
fuel.
of fuel. So that is something
Yes.
that we have to take care of. But um, well, so that is why, strictly speaking, they will be not equal. So to be precise, let's take care of that. But you know that it is roughly equal. That is what I wanted to just point out. To be precise, it will not be equal. So then I will
Yeah,
write.
but for this
Now I will
case,
come.
if we consider just the control volume, then it
Hmm.
doesn't look like hey, we are getting anything inside more.
Yeah, but the see in this you're correct. But the even in the book that is not specified properly. The thing is that it is a black box to us. That is something very interesting. See this part when this in this figure, this we have written. Well, you're right, but to be actually this is a black box, so I'll mark that. Let me color that. How do I color draw? Yes. So let me do that. It's a good point. Um, See, this is the black box. Okay, you don't know what is happening inside. It's only at the this dotted boundary that we know that there will be a pressure force. That is the intent of this diagram. The diagram's intent is not to say that we know the fluid flow or fluid field inside of it, that this is the flow field, that we are not drawing streamlines there or something of that sort. Okay. So it might be confusing, that oh, why don't we know that there is no well, in this case there is no mass addition, we know. But the thing is, to be precise, we don't know inside what is happening, we only know at the edges. Inside of it we don't know any details. That is the actual thing. There is a black box there. You get that, right? Or did it not make sense?
Yes, yes, but that means
You got it, right? So now uh, wait. So yeah, what is this? Acha, okay, now I have to, yeah. So me ve, right, minus dot mi by vi, and then what do we have, plus um, infinity. I know it's a little bit slow because I have to write the formulas and all, but I think it's okay. How do you have any questions from the lectures or something? Would you like to discuss something from the lecture?
no, no, no.
Okay, so let me just check if this expression which I have got is fine. If I have made all the bookkeeping I did, I was able to do all the bookkeeping. That is something I have to check. Not sure. So I think mi v infinity minus me v infinity. Okay. Infinity pe minus infinity ae. Okay. I think we're close. Let me just see. Because there is no one-to-one. I've not done it exactly from the book. So we are getting little bit different expressions. I guess that's okay. We'll move to the next slide. Okay. This slide has been on lecture 3. Yeah. So we have this expression. Let me move to the next slide. So a couple of things which I have to take care from the previous, I will have to take from the previous slide is this also. Okay. So just now simple substitution that we have to do. This is on fluid, this is on solid. So we do a minus sign, I guess, or not. Let me see. Wait, there's some issue, I guess. Fine. Wait. Minus sign. So now, what do you think? Can you go ahead and substitute anything here? Can you go ahead? Can you tell me what is the next step? Basically, it's a substitution. I'm just checking if um, all signs and all are correct or not, because we have very loosely treated signs here, which is not good. The thing is, we said that this is the pressure force, right? This is the on fluid, and we have minus of on solid. So this actually will become on fluid. And this I can remove. So we will have this term there. Plus AI term will get cancelled, I guess. What have I written? No. There's something wrong.
The
What is this?
area term
This term.
see
This is right? There will be a minus sign. Mistakenly I've written something wrong here. Wait, I see what I've done. This will be
that
PEAE. What have I written?
that
What was
that
it on
should
the
be
previous?
exit area, I think.
What?
The
Oh, you're not able to see the screen itself. You can tell me. I'm doing all those things on the other slide. Ah, stupid. This area I've done it wrong, right? Let me correct that. This will
uh,
be PIAI.
the
This will be this will be PEA,
uh,
right?
exit uh,
Let's move to the next slide. I did a bunch of things on the next slide. Let me just correct that. So here also I'll correct this. This is fine. Now, uh, we have this term here. Can you give me like 2 seconds? Yes, hello. Am I audible? And what screen are you with
yes,
looking at? Let me just check. Hello.
Yes, yes.
Yeah. So now you see this term you see, okay? This term. Now let's just do a simple substitution. Let's forget this. Let's do the substitution. Simple substitution only is left, nothing much. This is and one more thing I'll write. This is equal to one fluid, right? So what is this term? What will this term be? This term will be this, right? Is that okay? I guess. And if we were to take this minus sign inside, no, 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 no. So this is there, and this can be, yeah. So now this plus can be written as this. So why I'm doing this is you'll understand. You get that, right? What I just wrote.
Yes. Yeah.
Now we just substitute this there. Mhm. And this I will substitute from the above expression. What is it? Right? Now simple stuff. Let's just go ahead and substitute everything. This is there. What are we getting? We are getting this minus sign I will absorb inside. This will be plus. This will become minus. This will become plus. I think that's it. Right? Let me remove this. Okay. Now what expression? There is some small cancellation that can happen. This part will get cancelled. Okay. So you can just simply write. You see the cancellation, right? You see that there is a cancellation happening. P infinity A I gets cancelled. This term, right? And
Yes.
we can take AE common, AE common, and then there is a so maybe not very interesting to you, but it is a good thing. Think about what was the case when we had written the expression for the balloon. What the balloon we just wrote some expression. You see, this is the exactly what this is exactly the expression we had gotten in the case of the balloon. We the only the pressure contribution, right? Let me check if the expression final expression we have got is fine. The final expression is MEVE. Oh, seems I've done a mistake somewhere. Ah, interesting. So some mistake I have done. Let me just not go back to the exact thing, but we'll see. Or do you see a mistake somewhere? Can you spot a mistake somewhere?
I'm
This
just
is gonna
getting
be a
confused due to the minus and plus signs. Uh,
yeah, this is a little
I
bit
think
confusing. We have to
I,
do
I
it properly.
I remember that it was exit minus inlet. Like all the terms were exit minus inlet. Uh,
Exit minus inlet, is it?
yeah, yes. Some,
Yeah, so this is
but
a good,
I don't
maybe
know
a good.
where, where what happened.
It's okay, and this will be V infinity. There is some like it's a lot of bookkeeping. That's not the intent of this thing. There, we can always do it very formally, but again, then it becomes a lot of derivation. So I just wanted to do it quickly. This is the expression that we will get. There will be a minus sign and stuff. So there is something that we have not properly done and some minus sign we have forgotten. But the final expression is something like this. The whole point is that see, there's a pressure contribution because on the control volume on the fluid on the one end of it there is a small pressure on the exit and there is a higher pressure on the inlet. No, that's not correct. So see this negative pressure PE will be we discussed that PE will be lower than P infinity, right?
Yes.
Right. So that implies that has something to do with the velocity of the jet. Okay, the jet which is leaving, and there is also some contribution from the what do you call like for a rocket engine there is no inlet term, so the thrust comes exactly from this part,
Yes.
right? So that is the thing there. I think we can do a small problem. So maybe we can do a small problem. Uh, so maybe I also need to redo this problem. I did not do it very well, but it's okay, I guess. The whole intent was to just derive this expressions, show you that integral equation helps you. So the what was the whole point of this problem? See, if the whole point of the problem was not to do this uh, substitution and derivation. The whole point was this part of it, that rather than solving this very complicated expression which we don't know about, we know about some terms. We know about the velocities that are being exchanged from the control volume, and we also know the pressure at these volumes at these surfaces. So we can substitute for it using the integral equations. That is the whole point of it. Okay. So, anyways, um, the final expression is something that this is the final expression that we got. We, would you like me to solve a simple numerical problem on this, or should we move to a better another example of this same sort? What would you like to do? It's only 10 minutes left. But okay, let me discuss that problem with you. Okay, that's an interesting problem. Let me copy paste it, and we'll do it. And maybe if you're able to understand how to solve that problem, maybe the whole um intent or the intent of this today's class is kind of it is met. I think it is met. So let's do that. Let me see what slide do you see. Yeah, so you see this slide. Let me move to the next slide. Let me copy paste it. So this is from Anderson only. Okay, I'm not able to paste it. Yeah. So these are two questions. Okay, the first one is NASA exactly did this. They used integral equations to find uh, the drag, I think. Right. Yeah, the drag and the lift on a wing. Okay. So the whole point is, see, let's read it properly. So when the national this NASA measured the lift and drag of airfoil models, they made wings that spanned the entire test section. So they had this um, big test section, and let me draw it properly. So have you seen a wind tunnel ever?
Yes. I have. Yes.
Yes, yes, you've seen a wind tunnel. So let's move ahead. Then there is no point. So they had spanned the entire test section. The wingtips butted against the two side walls. So this is the tunnel. The wing would have like will be of this sort, and this will be the like trailing edge, and this will be the leading edge. Okay, this is the leading edge. This would be the trailing edge or something. Now, what did they do? They made it two-dimensional, so that there are no wingtip effects. Let's not look at what this wingtip effect. Do you know about what these wingtip effects are? So
Yes.
why
Yes.
would they do this? Why would they do this? Why would why would they not make it
They
less
would.
wider? Hmm.
Sorry. Sorry.
So
What?
it's written actually.
Hello.
Hello,
Hello.
hello.
Yeah. I think
So
I
I'm
lost it
saying, I'm
in the
saying,
last.
but I'll repeat it. That's okay. I'm asking what is uh, what is the principle or what is the idea behind making it such a long wingtip? Why not make it a little shorter in this lateral direction, not in the downstream direction or in the streamwise direction, in the cross stream direction? Why would they do it? Again, wingtip effects only. Whatever there will be no flow in this. So suppose if this is x,
think they
uh,
wanted
if this
just
is x,
um
this is y, there will be no flow there will be all flow in the z direction. The flow will be majorly in the z direction, but there will be no flow in negative x or positive x. So there will be at least those forces and flows we don't have to take care. If this is the case, then it becomes a little 2D kind of thing. Okay, so now instead of using a pitot tube, let me come back. Naka obtained the drag by measuring the velocity distribution behind the wingtip in a plane perpendicular to the plane of the wing. So now what they're saying is that this is the wing. Let me properly do it. Not like this. So if this is the wing, they did not measure the forces on this wingtip. What they did was downstream of the wing, they measured the velocity profile here. Downstream of it, much downstream. Right now, because I don't have space, I have drawn it like this. But they measured the velocity at this end and they measured the drag. What is the principle there? That is something that we can discuss. Okay, and similarly, they can also measure the lift by measuring the force on these walls. Okay, this is the second question. Let's briefly discuss this. If we can crack this, then I think it's done. Okay, so we'll look at it. We'll not look at the lift thing. Lift thing is a little simple only. It's not a big thing. In fact, we'll see that this lift wala part. The point is that you can measure the lift on the wing by just measuring the force on the top and the bottom wall. Okay, you can measure the drag by measuring the velocity profile at far downstream. Okay, lift wala part we will not discuss because again by just looking at the force balance we will see that the force applied on the wing will be equal to the force applied by the wing on the fluid, and that will affect the pressures on the top and the bottom wall, and from that we can calculate. Okay, anyways, let's look at this drag problem. That is a little problem which aligns better with that this jet propulsion problem. So let's look at this. What do you think like will velocities be higher, lower? What is the physical idea of these velocities? If this is u, uh, will it be uniform? Let's ask this question. Will it be uniform? And
won't be
suppose give this is u. It won't be. Why?
won't be. Um,
Why?
According to my knowledge, so over an airfoil to get a pressure differential, like the pressure uh, below the
Yes.
airfoil, it needs to be higher, and above the airfoil, we get a suction region, right, and low pressure.
Yes.
So
But far
to get a
downstream. The point is okay. Let me.
so
So this is the tip, and
the
I'm going here. It's very far. Suppose. Now you tell me. This is U
we say
infinity.
it's very far, like at some infinity distance, then it would be equal actually.
Will it be
It
uniform?
yes. If we consider very far, then but if
Uh,
some finite distance
and
is
that
considered,
is coming from your intuition that far field, the airfoil cannot affect every part of the fluid. Far away from it, its effect is gonna die. It is gonna die. That is your argument, right?
uh,
Did you did
actually the 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 velocity over the airfoil, that would be like a, it would be faster. So the fluid would flow faster over the airfoil, and it would go slower below it.
suppose it's not airfoil? Let's say it's a sphere. It's a spherical
If we
thing.
consider
Now
infinity distance, then it would be like uh, it we wouldn't see any perturbations actually. much
Perturbations.
significant.
I- why would perturbations come in this? Why did you say perturbations? Any reason?
Oh no, sorry.
Let's
No,
say
no.
it's a sphere. Hello. Hello?
Hello?
Yeah.
No, no, no. Nothing. I think I
So
lost
there are
the
two
signal.
things which you said. Let me move ahead. Let me tell you, because I wanted to briefly discuss this. Okay. First of all, it's very interesting when I said far field, you agreed with me and you said no, velocities will kind of become uniform, which is very interesting, and that is exactly what happens. Because the wing cannot affect the fluid very far from it, it makes sense to just treat it as u infinity. In fact, very far from it, it has to be close to u infinity, right? Close to u infinity, isn't it?
Yes.
Just give me a second. But it turns out the farther away you go, the fluid. So basically, for a sphere or for this thing also, what you were talking about would mm,
I think it
well, I
I
can't
think
say.
I was
Huh.
thinking about non-viscous sorry, non-viscous I was saying non-viscous.
Okay.
Inviscid flow, sorry,
Con
inviscid
consider
flow. I
it
was actually
inviscid. Consider
imagining
it inviscid.
yes,
Consider
yes.
it inviscid. Now tell me. Interesting point that you made. Inviscid come into the
If it is
very
inviscid, then
interesting.
it would be uniform. Like at very
It will be
far,
uniform.
yeah, means near to like
Then
that.
there is no drag only. Yeah. Then there is no drag only.
Hmm.
Good.
Hmm.
Then there is no drag only. Now consider that there is this inviscidity, there is this viscosity there. Now tell me.
Then there would be turbulence.
Then there will be turbulence, you say.
Yeah.
But let's say,
At
what is
that
the mean uh, steady velocity? Let's suppose it's laminar. Let's say I maintained laminar conditions. Now what?
then uh, we would eventually uh, for viscous flow, right?
Hmm.
For viscous flow, we would get some distribution. Like above the center line, we would get a little bit faster flow, and below we may get somewhat slower velocity.
Okay. Maybe there is a little bit. Why are we considering it as a wing? Let's consider it as a sphere so that you don't have any issue with the symmetry of the problem. Why do we complicate the problem? Let's say uh it's a sphere. Now tell me. So there is no upside or downside of it. Now tell me. But like this is one easier way to think about it. We can move once we solve the issue with the sphere, then you can go ahead and think about the wing. That is another level of problem that we can do. Tell me. For a sphere, what will happen?
For viscous flow, yeah. So near near the center line, um,
Near the
we
center
would
line,
okay, it goes
it will be of
faster.
something this
It
sort.
goes
Is it gonna be something of this sort?
yes, yes.
Farther away as we go, this will become
It would like a
something of
little
this.
bit straighten up like that.
Yeah, and slowly it will become uniform. So it's called
Yes.
wake of the object,
The wake. Yes,
right?
yes. The wake.
Wake of the object.
Flow detach. It gets
Yeah,
detached.
well, not well, no, not detached. I said the flow is laminar. In laminar flows, in truly laminar flow, there's no detachment happening. Okay.
Okay.
Detachment as
Oh,
soon as the
oh, oh.
flow uh once the flow detaches, no, this laminarity is violated. I
Yeah. Okay.
guess. I have to think about it. Yeah. Once the flow is laminar, your equations are not valid. Yeah. So there's this
Yes.
wake.
Okay.
Okay. Now you only told me that it will be lower towards the center line and it will slowly it will be reaching the infinity, u infinity, approach infinity. Now suppose, um, see, you see here, there's a velocity deficit, right? Sorry, mass velocity deficit. You see that there's a velocity deficit, right? In this part of
Yes.
it, this is a velocity deficit, isn't it?
Yes. Yes.
Isn't it?
Yes.
How can you possibly recover this velocity deficit? You can't recover it, right? You lost some velocity at this control volume. Suppose this is my control volume. This is no, not this. Wait. To draw it properly, not like this. Let me move on to the next slide. Yeah, this one only. This is my sphere. I take a small control volume. I know the velocity profile is something of this sort. There is some flow that is going to happen here. This is u infinity into some length scale. Okay, u infinity into L. I know this velocity, this mass flux is lower than u infinity because you said there is a velocity deficit. This would have been u infinity, but we know that u is lesser than u infinity in certain regions of L or something, right? This is L. Where is the extra mass going? How can that possibly leave the control volume? Where is the extra mass leaving?
Maybe the dynamic pressure is getting converted to static pressure somewhere. Like,
That is fine,
you
but
know,
even then,
the
hmm, yeah,
means
go ahead.
just behind, uh,
Hmm.
uh, just behind the sphere, we would get some like uh, a bit of turbulence in
I
that
suppose I'm
asymptote
saying
like
Reynolds number
region.
tends Reynolds number is much smaller than zero. I'm saying sorry, much smaller than one. It's tending to zero. There is no turbulence. Consider there is no turbulence. See, turbulence complicates our issue. I understand why you are trying to think. You're trying to think it in a very real sense. You're trying to figure out. But I am telling you that the real problem is a much more complicated than uh, to it's much more complicated to be solved by the tools we have right now. That is why I'm always, whenever you say turbulence or whenever you're going into directions of asymmetrical flows, lower velocities on the lower phase, so higher velocities on the lower phase, lower velocities on the upper phase. Uh, the tools we right now have are incompetent to solve these issues. That is why I'm trying to direct you towards the simpler problems. So that is why I'm saying consider there is no turbulence in anything, but the flow is inviscid. Oh, sorry, the flow is viscous. In inviscid flow, what will happen? There will be 100% recovery of the flow. So it will be U
Yes,
infinity totally. That is gonna happen, right? This will be 100% recovery. But in inviscid flow, there will be a wake. So that it's called a wake, and you can have a laminar wake also. Basically, what happens is you move some mass out of your control volume on the from the top edges. So there will be some mass leaving this top edge. And if you define your control volume smart enough, if you define it very far away from it, like this, you know the u velocities here are gonna be u infinity. Pressure will be p infinity. So you know that there will be some velocity v which has to compensate for this velocity deficit. So that mass gets conserved first of all. Okay, so there is this velocity v which we need to calculate using mass conservation. That is the first thing. Okay, that is step one. If you would like, we can do this problem next time because now we are out of time, so I don't want to continue. But we can solve this problem anyways. I'll just tell you how to solve it. Okay, so first of all, we'll calculate this velocity. The first point of this whole discussion was if you have a wing span or anything, or if you have a wing or anything, that wing is going to displace mass out of this rectangular control volume. Okay, it is gonna because there is this wake which enters the picture. Even in the turbulence case also, now I am telling you in the turbulence case also there will be some velocity, some mass which is gonna leave the control volume. See, no matter what happens, mass is gonna get conserved. if static pressure becomes dynamic pressure, if there is energy loss, there is viscous effects, there are no viscous effects, mass though will get conserved only, right? Conserved, right? Mass cannot get converted into something else. There is only mass conservation. There is no, and like energy gets converted into pressure or kinetic, but mass is mass. So it has to be conserved, and it will. Uh, there will be some removal of mass in this direction. There will be a v velocity that these spheres or any object will induce first of all, and they will also carry some momentum with them. Okay. Now solving the conservation momentum of conservation equation on this body, we'll find out what is the force on this control volume. So the control volume will be looking like this. Let me erase. Yeah, is this entire thing. So control volume will be looking something like this. You're getting my point, is it? Fine, you're
Yes,
following.
yes, I'm getting it.
So I'm saying the control volume has to be of something of this sort. That around the sphere, this is the where this is the part where we will say that the force applied on this, there will be some force applied on this fluid. So I'm not drawing it properly. Let me draw it properly. So the solid will apply some force on this fluid boundary. Okay, and that force, when using Newton's law of the third law, we can say what is the force on the solid body. Okay, the other part of the control volume will be this. Okay, there will be some mass which is gonna leave from these edges. We're gonna calculate that. There's a momentum that we can calculate, a momentum that they're gonna carry. That momentum will be roughly equal to, that the velocity here will be roughly equal to u infinity. That is one assumption that we will take. Why u infinity? Because it is very far from the wall. We don't expect uh, the wall. We don't expect the ball or the sphere or the wing to affect the velocity very far from it. So that is why we have to very carefully take the control volume very far, like very long. It cannot be very this thing. And in fact, even in this case also, it cannot be very far, very close also. Otherwise, what will happen is, another assumption that we need to take is, on this surface, the pressures are always P infinity. So that we don't have to take care of the pressure distribution near the sphere or the wing. And as you know, at the inlet also, we know that the boundaries, we would at the inlet we would know the pressure and velocity, right? Here we are calculating velocity profile. We are measuring the velocity profile on this edge. That is the whole point of it. So if I go back, they say that they measured the drag by just one measurement, which was the velocity measurement at the very downstream of it. See, so measuring the velocity distribution behind the wing in a plane perpendicular to the plane of the wing. So the plane of the wing is this paper or the screen, and perpendicular to it will, if this is XY plane, then the measurement they did was in the direction of XZ. This will be the plane perpendicular to XY, right? So they measured this velocity, this velocity distribution. I know this because I have solved this problem. That is why it might be a little confusing to you which velocity are they measuring. But I'm telling you that they measured this velocity distribution. That distribution I was like we were talking about just before of that.
Yes,
Far
yes.
from it, see, far from it, it will be a little close to u infinity, or it will be a little very uniform, not u infinity. It will be lesser, but it will be a uniformish thing. There will be a velocity deficit definitely, and by that velocity deficit, it will be so it will be something of this sort. If we go very far away from it, at the inlet it is u infinity. If you go very far downstream, you will have some small deficit, which will be not u infinity, something smaller. But that does not matter. It can be also some wavy curve. It will be actually wavy only. We measure this. We whatever we did in the case of the engine, we'll do the same thing there. We'll substitute for this term, this wala part, by putting all these things in together and get one expression, which let me write it for you. If you would like, you can go ahead and solve it and see if you can get to this expression. Okay, so let me just write this expression. the expression you're gonna get is the drag. Where is it? Just just give me a second. Yes. Hmm. So no, not this. Yeah. So the drag, let's say D, will be proportional to integral 0 to y. Well, this integral on AB u and u infinity minus u dy or dy. Where what is AB? Let me mark that AB for you. Okay. Proportional I have put in because there will be some constant. I'm not putting that constant right now. Um, yeah, come here now. Yeah. So suppose the control volume we take is of this sort. This is the ball, and the control volume we take is this. This is our AB, and we will integrate it over this surface, and we'll see that whatever velocity deficit we'll have will contribute to the drag. You see, I told you that this ball is gonna shift mass away from this control out of this control volume, right? Out of this control volume, this ball shifts moves some mass out. This mass out takes some momentum with it. This is exactly it will this the momentum it takes slows down the fluid around the wall. That fluid equivalently applies the same force on the fluid. See, the fluid is getting slowed down because some momentum has left the control volume, which implies that to reduce the momentum of some fluid, you need to apply some force. That force is exactly the drag force. To get that idea, the reasoning why this will come.
Yes. Yes.
So we'll have to do it again more properly. We can do it. I'll try to do it next time. I'll see. Yeah. So do you have
I
any
think it's
questions?
just
Was it clear? Yeah.
oh, sorry.
No, go ahead.
No, it just I was saying just momentum conservation, right?
Yeah, this one is just momentum conservation. This is just momentum conservation.
Yes.
The whole point was, see, otherwise, what is the point? How do you calculate drag? You calculate the pressure, the force on the either you calculate pressure forces on the ball or on the wingtip. You'll have to put pressure taps here everywhere. You measure the pressure everywhere, okay, right? And then you see there will be pressure taps everywhere, and you integrate over those pressure values. That is called what is it called? If you would have seen, there are wing profiles. You'll see that there is a pressure varies like this. This
Yes,
is
yes,
P
I've seen
infinity,
it.
right? That is how we calculate. This is the lift, and there are some drag effects also. That is how we calculate this. If we have to locally calculate it, if we have to integrate over the surface of the body. But if we don't have to, the power of the integral equation is we can solve for a larger control volume and figure this one out by substituting this. So it is in principle a momentum conservation only. The only thing is that you have to do it properly, which we didn't do in today's lecture. We have to do it properly in the sense that all bookkeeping has to be done nicely so that you don't get wrong answers like we did. So sorry about that. You have to do it properly. Then you have to know what is going on physically. Also, you should be able to understand why why the drag depends on velocity deficit or something of that sort. Even in this case, there's a total reason why we get drag. The reason is that you're moving some, you're giving some air extra momentum. This is extra momentum, okay? And this is the extra pressure force you're getting. What is this happening? Why is this happening? This is the extra force term. So we'll see on the when we integrate because one edge has a extra this lower pressure. You'll see that that also contributes to the thrust. That is the whole idea. We have to so that I will do right now. I don't have I can't do it properly because I don't to see. I also don't, I can't correlate what exactly these two terms mean. This one means extra momentum. I'm not able to figure this one out. I'll see how this term, what does this term physically mean? Okay, but there's a physical meaning associated to this term also. So these were some couple of points which I wanted to just this was the whole intent of it. So I guess yeah, that's all. If you have any questions, you can ask me.
No, no, I don't have any right now.
Yeah,
I may have in maybe I may ask in the next lecture.
fine.
Yes.
And by next time, I also figure this one out. Yeah, good, great, Pranav. Nice. It was nice talking to you. Like for the entire meeting. Great. We'll meet next time. Thanks.
Thank you, sir. Yeah, thank you.